since this sometimes generates confusion and is sometimes not so well understood, let us indeed go through this exercise once again. And we will look at the usual routine calibration graph of a usual routine analytical procedure, and we will try to see how this fits with the definition of calibration. So, whenever it is some kind of instrumental analysis, there's some kind of signal or analytical response that we measure, that I have denoted by A. And this signal is dependent on the concentration of the analyte in the sample, which I've here denoted by C. And now, the usual way is that people prepare calibration samples or calibration solutions from the pure analyte. So, from the compound that they determine and the solvent and possibly some other additives, they make solutions, a set of solutions where the analyte concentration is known very well. And these solutions can have concentrations such as C1, C2, C3, C4, for example. And now what people do, they make analytical measurements with all these solutions, meaning they measure the signal or the response corresponding to this particular analyte in those solutions using the instrumental technique that they use. And they get values such as A1, A2, A3, A4. And now they make calibration graph at the intersection of all these concentrations and measured values. They make points. And by connecting all these points with a straight or curved line, they get the calibration graph. Now, let us now go back to the definition and see where we are in terms of this definition. So, see, as a first step, establishes a relation between the quantity values with measurement uncertainties provided by measurement standards. So, what are measurement standards in our case? No, standards. Concentration cannot be a standard. Calibration solutions, yeah, these are our measurement standards. In order to make it even more visual, let me draw that we really have some volumetric flasks where the calibration solutions are inside. So these are our measurement standards, these solutions. All right. Now, values with uncertainties. What is the value, or what are the values here? Where are the values?
The signals we painted in the
Is it?
like the exact value, the points, what's it?
We speak about the quantity values. What are the quantities that we are actually measuring when we make chemical analysis? Concentrations. Yeah. So the quantity values are where? So I've indicated here different kinds of values. Which ones are the quantity values according to this definition? Exactly, the concentrations. All right. quantity values. I did not write uncertainties at the moment, but well, we all know that they have to have some uncertainties, but simply not to make it too crowded, let us leave uncertainties aside for a moment. Now there comes the next phrase, and corresponding indications with associated measurement uncertainties. So what are indications? Yeah, the responses, the A's are indications. And now establishes a relation. Do we see a relation here on this graph anywhere? And where is the relation?
Calibration graph.
Splendid. Yes, so it is. So this here is the relation. Is there any other way of writing this relation? What do you think? At the moment, it's a graphical relation. Can we give it a different form?
With slope and intercept.
Yeah, exactly. A is equal to B0 plus B1 times C. This is also relation. As you know, different models and relations can be oftentimes expressed either graphically or by a formula. So this is the different way of expressing this same relation. Yeah. Okay, I think we've pretty much gone through the first step now. Are there any questions at the moment? Okay, please raise your hand who thinks that this first step is understandable to you in terms of a calibration graph. Good. Now the second step uses this information to establish a relation for obtaining a measurement result from an indication. How do we go now? What do we do now? So we already have one relation. What other relation do we need to establish? Okay, let me ask you this way. What could this mean? Obtaining a measurement result from an indication. What kind of indication? What could they have possibly thought in this case?
From the signal, we find the concentration of our sample solution.
Yeah, our sample solution. So now we take a solution where we do not know how much of the analyte is inside. Yeah. So, and we get some kind of indication which we denote by AX. The signal corresponding to the unknown concentration. And now, from this graph, we can find the concentration of the analyte in that sample solution denoted by Cx. But now, to establish a relation for obtaining a measurement result from an indication, what could that mean actually? We have a relation, no? What else can we do?
Apply this relation?
Yeah, in principle, yes. We now write it like this. Cx is equal to A minus B0 divided by B1. Yeah. And instead of A, let us write AX. So this is now a relation for obtaining a measurement result from an indication. This here.
But there might be another situation like the calibration curve is not linear.
Oh, and in that case, it's not a linear function, but maybe some quadratic or cubic function, or maybe logarithmic or something. But in any case, we need to express C from here. In very difficult cases, it can happen that we do not have an analytical expression, but then we can numerically solve it for C. That is also fine. In principle, we also can sometimes be satisfied by graphically finding, but this is not really very often done these days. So linearity is not obligatory here, although it's desirable generally.